electronic configuration as well as explain periodic trends on the periodic table. Right. So just to remind you, when we are looking at electronic configuration, I mentioned that there are 3 principles which you need to be conversant with. You need to be conversant with the Aufbau principle, you need to be conversant with the Pauli's exclusion principle, you also need to be conversant with the Hans rule. These 3 principles will help you to actually understand how to write electronic configuration of atoms. Okay, so a quick reminder on what the Aufbau principle states. The Aufbau principle states that orbitals of lower energy will be occupied by electrons first. Okay, so this one, we mentioned that orbitals of lower energy will be occupied by electrons first. Right. Then just move this so that you are able to see clearly. And when considering the Aufbau principle, we also referred to what is known as the N plus L rule. Okay? So this is just to remind you what we covered whilst you are on campus. Okay? So I said you use the N plus L rule. This N plus L rule will help you to actually determine which orbital will be occupied by electrons first. For instance, if you are given the 3s orbital, and I ask you, between the 3s orbital and the 3p orbital, which one will be occupied by electrons first? So, using the N plus L rule, which also springs from the Aufbau principle, you actually note that M here will be 3, L here will be, since it's the s orbital, L will be 0. Remember, I mentioned that N is the principal quantum number. It shows you the energy level of the orbital. It also shows you the size of the orbital. L is the angular momentum quantum number. This principal quantum number shows you the shape of the atomic orbital. And I showed you a simple table to help you identify L values for different orbitals. If you remember, so I can just write that simple table here. Okay? So we have the S, P, D, F, etc. Then here we are looking at the L values. So when L is 0, it's the s orbital. When L is 1, it's the p orbital. When L is 2, it's the d orbital. When L is 3, it's the f orbital, etc. Okay, so using this simple table, you can actually tell which one is the L value. So meaning here, N is 3, L is 0. Okay? So, the sum of this is actually 3. Then you come here, N here is 3, L here is what? So since it's p orbital, L is 1, therefore the summation of that will be 4. Okay? So what does the N plus L rule state? Okay? The orbital with the least number of N plus L, the sum of N plus L, will be occupied by electrons first. So in this case, since the orbital with the least value of N plus L is 3s, it means that the 3s will be occupied by electrons before the 3p. Okay. And this actually eventually tells you that the 3s orbital has lower energy than the 3p orbital. If you actually went on to look at your Orbital diagram, you see that the 3s orbital has lower energy as compared to the 3p orbital. Okay? So this is the first principle which we discussed, and I'm just reminding you what we did. Okay? The next principle we're going to look at is the Pauli's exclusion principle. So I'll wrap this. Right. And when you look at the Pauli's exclusion principle, it tells you that no two electrons in an atomic orbital will have the same set of the 4 quantum numbers. Okay? No two electrons in an atomic orbital will have the same set of the 4 quantum numbers. Right. So if I was to write that down, so I'll say let us look at an illustration of what this principle entails. So let us look at, for instance, I'll pick maybe a 2s orbital. Okay, and if you want to load electrons in this, okay, what this principle says is, of course, we know that the maximum number of electrons an orbital can accommodate is 2 electrons. Okay, so what this principle says is, if you load your electrons in here, it means that one electron will have a positive spin, the other electron will have a negative spin. Okay, because no 2 electrons will have the same set. So for instance, if I was to draw this, okay, please take note. If I was to draw this, this is, it's not following the Pauli's exclusion principle. Because if you look at this illustration here, which is wrong by the way, if you have electron A and electron B, okay, the quantum numbers, of course, we know that there are 4 in number. There's N, there's L, ML, and MS. Okay? N here stands for the principal quantum number, which is actually the energy level. Okay? So N here is 2. We come to L. L here is what? 0. Looking at the table I showed you earlier. Okay? If you have to determine your ML values, okay, how do you actually determine ML values? These are values obtained from using the L value. Okay? So total ML values is 2L plus 1. 2L plus 1 values. Okay? 2L plus 1 values. So since L there is 0, so it will be 2 times 0 plus 1. So it will be 1 value. Okay? This is the maximum number ML values this orbital can have. And then for which one is that one value? Okay, because we know that ML values can have values from this possible set, can have values, okay, from -1, 0, and +1. Okay, can have those integral values. So since it's one value, the maximum ML value here is one value, it means that we're actually looking at the starting point itself, so the ML value there will be 0, right? Then, what's a spin? Spin quantum number. Okay, so spin quantum number shows you the direction in which your electrons are pointing, either clockwise or counterclockwise. And since both of these are actually pointing upwards, okay, meaning they are pointing in the clockwise direction, so it means electron A has positive half, electron B has positive half. So you see that this is the same set. Okay, it means these two electrons, according to this arrangement, have the same set of these. So these are violating the Pauli's exclusion principle. Because Pauli's exclusion principle says that no two electrons in an atomic orbital will have the same set of all the 4 quantum numbers. Okay? So what does this tell you? This tells you that when you're arranging electrons in an orbital, one electron will have a positive half spin, the other one will have negative half spin. Okay? So I'm just reminding you what we covered last time. Okay? The last rule is Hand's rule. Right. So when you remember on Hand's rule, we mentioned that according to Hand's rule, electrons occupy orbitals of the same energy in a way that makes the number of parallel spins maximum. Okay, so it favors same spin direction. Okay, so if we were to write that, you say electrons So electrons will occupy atomic orbitals with same spin direction, that is parallel spins, before filling with the opposite spin. Alright, so now to illustrate this, let's see if you have 3 electrons and you want to fill them in the p orbitals, the 2 p orbitals. You remember, p orbitals are 3 in number. Okay? So we have 3 orbitals and we have 3 electrons want to occupy this orbital. So what this rule entails is you actually maximize parallel spins. So you put 1 electron there, go to the next orbital, another electron, then the 3rd electron will go to the 3rd orbital. Okay? So this is the correct way of actually filling this orbital. You do not do this. This is wrong. Okay? So according to Hahne's rule, electrons occupy atomic orbitals of same energy. Remember, this is same energy. Okay? So atomic orbitals of same energy, okay, they will occupy the same spin direction before you start filling with the opposite spin direction. Okay? So since these orbitals are degenerate, there's no way you can leave this orbital empty and completely fill this one. Okay? So this is the wrong way of filling their orbitals, and this is the correct way, according to Hahne's rule. Right. So now we've looked at the 3 principles, which are a guide to come up with electronic configuration. Okay. So now we'll now move on to now how to come up with electronic configuration of elements. We'll pick on, for instance, oxygen. Okay? And a simple guide to coming up with electronic configuration is actually using the Orbital diagram. Okay? So you write your Orbital diagram. It is as simple as I'm doing right now. Okay. So depending on your number of electrons, you write your Orbital diagram in accordance to that. So the simple guide is to use what is known as the diagonal rule on your Orbital diagram. And what does this rule state? Few electrons following these diagonal arrows. Okay. So looking at this nuclide, electrons here is 8. So since it's neutral, it means the number of electrons here is equally 8. And if you now want to write electronic configuration, which is basically the arrangement of electrons in atomic orbitals of these atoms, okay, we'll start by following the direction of the arrows, since we are using the diagonal rule on our Orbital diagram. So it means the first electrons will fill the 1s orbital, so it will be 1s2. And why are we saying 2? It's because an orbital can occupy a maximum of can be occupied by a maximum of 2 electrons, right? And then the next electrons go to the 2s. And how many electrons occupy that? It's 2. So we've already distributed how many? 4 electrons from the 8. We're remaining with 4. So the next will go in the 2p. And how many electrons, maximum number of electrons which the p orbitals can accommodate? Since we have 3 p orbitals, okay? We have 3 p orbitals. It means each of these can actually have 2, 2, 2. So p orbitals can actually accommodate a total of 6 electrons. Okay? And for the s orbitals, we only have 1 s orbital. And 1 s orbital can have maximum of 2 electrons. Okay? So that's why we have a maximum of 2 electrons there. Now, since we have distributed 4, we are remaining with 4. This can have a maximum of 6. So it means the remaining 4 can all fill the 2p orbital. And this is our electronic configuration. Okay? So this is the expanded electronic configuration. Okay? So this electronic configuration, we can have an expanded electronic configuration. We can also represent this as orbital diagram or orbital notation. You can equally represent it as noble gas configuration. Or abbreviated. So what we just say noble gas configuration. Okay? So let's represent this in these 3 ways so that you are able to actually see how we can represent this in these 3 forms of electronic configuration. So like I said, this is our expanded electronic configuration. This one is, okay, so this is expanded, so let's represent it as orbital diagram or orbital notation. It's the same. So orbital diagram, it means that we are now displaying this as, you have to draw the atomic orbitals. Okay, so how is an orbital represented? An orbital is represented using either a line or a box. Okay, since you can't go around, writing shapes of orbitals, the s orbital is spherical and stuff like that. So to simplify orbitals, you can either use a line or a box. So I'll use a line myself. Okay. So I'll start s orbitals. This is 1. Okay. How many electrons are in the s orbital? 2. And according to Pauli's exclusion principle, these orbitals will be filled in as shown on the board. Because no two electrons in an atomic orbital will have the same set of the 4 quantum members. So one, they will differ. They can have the same N, L, and ML value, but they will differ in their spin. Okay? Go to the 2s. The 2s also has 2 electrons as shown. We go to the 2p. Okay? How many electrons are in the 2p orbital? There are 4 electrons. So here we use the hand rule. Okay? So you maximize parallel spins before you start feeding with the opposite spin. So since this is the these orbitals are all in the same energy level 2, it means they are degenerate, and as such, electrons will occupy same spin direction up to the end. And if you have extra electrons, you can come back and start filling with the opposite spin direction. So which is that? Okay, so this is the orbital diagram. Right. And then we now represent this using noble gas configuration, or the abbreviated electronic configuration. So when you are considering this, we have to look at the noble gas, which is just preceding oxygen on the periodic table. Okay, so I'll just pick my periodic table. So now when you look at oxygen, in this case, we have no noble gas preceding oxygen, okay? Because we look at the noble gas just before, okay? So it means we have no noble gas core there, right? So we leave it at this, okay? But for us to show this configuration very well, let us look at another element. Let's pick, for instance, calcium. Let's look at calcium. Okay, so we see that here, number of electrons is 20. So let's look at the expanded electronic configuration. We follow the same Orbital diagram. Okay, so the first electron will go in the 1s, so it will be 1s2. The next electrons will go in the 2s, so it will be 2s2. The next electrons will go in the 2p, 2p6, since p orbitals can have a maximum of 6 electrons. Then the next electrons will go in the 3s. How many? 2. So from up to here, we have already filled 10 electrons. We're remaining with 10. So after 3s, the next one is 3p6. So here, that gives you 8. Then 4s, 4s2. Okay, so that's our expanded electronic configuration, right? Then next, we can now write what is known as the orbital diagram, or orbital notation. So orbital diagram or orbital notation, you actually draw the orbitals and represent how electrons are arranged in these orbitals. Okay, so the first one is 1s orbital. There's 2 electrons following the 3 principles I earlier alluded to. Then we have the 2s. There's 2 electrons. Then you have the 2p. There's 6 electrons. Have the 3s, 2 electrons. Then have the 3p. There are 3 in total. So six. And the last one is 4s with 2 electrons. So this is orbital notation or orbital diagram. Okay. Now we can now represent this using noble gas configuration. Noble gas configuration. So you go to your periodic table. You go to where calcium is. Okay. Calcium. So look at the preceding noble gas. Preceding noble gas for calcium is argon. So you have argon core. Okay. Then, so you note that argon has actually 18 electrons. So meaning this whole electrons from 1s up to somewhere 3p, all these electrons are actually in the argon core electrons. Okay. The only electrons which are outside that is the 4s2. Okay. So this is an abbreviated version of electronic configuration for calcium. Okay. So what does this mean? These are your core electrons. These are your valence electrons. These are your valence electrons. And you remember when you were saying, when you're learning about bonding, you note that the electrons which are used are the electrons in the valence shell, which is the outermost shell. So this is the valence shell. So even when calcium is reacting with another element, it's these electrons which are used in bonding. Okay. So you should be able to represent your electronic configuration as an expanded electronic configuration, or as orbital diagram or orbital notation. We can also represent it as noble gas configuration. Okay, so refer to your notes. I uploaded notes on Moodle so that you're now able to follow through. Right, and if you have any questions, you can actually forward your questions via the platform, various platforms which have been given to you, and I'll be able to address them. Right. So this is how you actually come up with the electronic configuration. The next thing we'll look at exceptional cases. So under exceptional cases, we note that using the alpha diagram, you can actually obtain correct electronic configuration. You can obtain correct electronic configuration up to element 23. Okay. Up to element 23. So which one is element 23? That's vanadium. So you can use the alpha diagram to obtain correct electronic configuration up to vanadium. Right. So after which there are some exceptional cases which are notable. And notable ones include chromium and copper. Okay, these are the notable cases. Okay, so you see that chromium has 24 electrons, copper has 29 electrons. So if you use your alpha diagram, which we can actually draw, so that's 1s, 2s, 3s, 4s, 5s, 6s, then you have 2p, 3p, 4p, 5p, 6p, then you have 3d, 4d, 5d, and 6d. So using this Aufbau diagram, okay, and following the direction of arrows, you can actually come up with the electronic configurations, but it gives you incorrect electronic configurations. Okay, so if we start with chromium, so it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay, so let's see how many we have distributed. So this is 10, 10, that's 20. Then the next orbital is 3d, and how many? 3d4. Okay, this is the predicted electronic configuration according to the Aufbau diagram, and of course we see that it gives an incorrect electronic configuration, and we'll explain that later. Okay, so copper also have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d9. Okay. So these are incorrect because now we look at those arrangement. Because now there's an introduction of d orbitals in this electronic configuration. D orbitals are actually more stable. Okay? The stability of d orbitals has to go with the how electrons are actually filled. So with d orbitals, okay, half filled and completely filled. Completely filled d orbitals are more stable. Than any other configuration. Okay? Because now there's an introduction of d orbitals. So d orbitals are more stable when they are half filled or completely filled. Okay? So what does this mean? It means this configuration is not favored. Okay? This is the predicted configuration following the Aufbau diagram is not what? Favored. So which one will be favored? The one to be favored is the half filled in terms of chromium. So this configuration will hence appear as 1s2, 2s2, 2p6, 3s2, 3p6. Okay, so one electron from the s orbital will go and fill the d orbital, so it will be 3d5 and 4s1. Okay? And when it comes to transition metals, because copper now is in the D block, which is the first row of transition metals, the 4s orbitals always appear as valence electrons because of when electrons occupy this configuration, the 4s orbital becomes with less energy than the d orbital. Okay. Then the copper configuration will also appear as follows. So it will be 3d10 and 4s for S1. So this half-filled orbital will be more favored than this incompletely filled d orbital. So this configuration will not be favored. The configuration which will be favored is the one which has 5 electrons. Also, the completely filled d orbital is more favored than the completely filled d orbital, which is d9. So this configuration will be favored, and this is what the electronic configuration of copper is. So if you are asked to explain why you get incorrect electronic configuration by using the Orbital diagram, it's because of the inclusion of d orbitals, whose stability depends on whether it's half-filled or completely filled. Okay, so I think this does it in terms of electronic configurations. We'll now move on to periodic trends. So refer to your notes. Okay. Refer to your notes, which are uploaded on Moodle, so that you are conversant with the topics being discussed. And if you have any questions, you can always post on your various platforms so that we address them. Okay, so now look at periodic table and periodic trends. So the trends we'll be looking at include the following. One, we look at atomic radius and ionic radius. We'll also look at ionization energy. We'll also look at electronegativity. Okay? So, by trends, basically, of course, when you look at your periodic table, so you refer to your notes so that you are able to see what I'm talking about. So of course that you know that the periodic table has a total of 18 groups, or with the inclusion of the D block elements. Okay, but if you remove the D block elements, we have 8 groups. Okay, so from top to bottom, these are your groups. So this is group 1, group 2. Okay, so if we leave out the D block, so this is the D block elements. These are the transition metals. So we have then 8. Okay? So you know that this is really just S block elements. Why? Because the S orbitals are filling, or the S orbitals are the ones being occupied by electrons. These are called the D block elements because the D orbitals are the ones which are being filled up by electrons, or D orbitals are filling up with electrons. Then you have the P block. Okay? So to make it clear, P block elements, then we have these two series which are known as the lanthanides and the actinides, or F block elements. These are known as F block elements because F orbitals are filling. Okay, so just a quick review on your periodic table. You note that periodic table comprises of groups and periods. Okay, so we have 8 groups, as I've said. We have these 8 groups, so there are 8 groups and 7 periods. Okay. The vertical columns, the ones which run from top to bottom, are your groups. Okay, vertical columns are your groups, and these horizontal columns are your periods. Okay, so what runs from top to bottom, these are your groups or your vertical columns. Okay, run from top to bottom, so you can count. This is group 1, group 2, group 3, group 4, group 5, group 6, group 7, group 8. Okay? When you leave out the D block elements. And then the horizontal rows, these ones, which run from left to right across a period. So these are periods. And we have 7 periods. Okay? So you can look at your periodic table actually. So when you're looking at your periodic table, then you can tell. If I was to write the periods, I'll just draw them in the first. So this is 1, 2. So these go across. Okay? We go across up to that far. Then so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7 periods. So these lines which run from left to right are called are known as periods. Then the vertical lines from top to bottom, these are known as groups. Okay. And then some groups have notable names, okay, which we're going to look at. But then the other thing you may need to note is when you move from top to bottom, you are actually increasing the principal quantum number, okay? Because you are feeding orbitals in a new energy level as you move down, Okay, so you see that these elements here have energy level 1, this is 2, 3, 4, 5, 6, 7. Okay, so meaning you are as you move from top to bottom, you are actually introducing electrons in new energy levels. Okay, so meaning the energy level is increasing as you move from top to bottom. Okay, then the other thing you will note is group 1 elements are known as the alkaline metals. Group 2 elements are known as the alkaline earth metals. And then the other notable group is group 6, which are the chalcogens, halogens, and noble gases. Okay. So these are your alkaline metals. These are your alkaline earth metals. Of course, several other names you in your reading which you may come across. Okay, like for instance, these are the phenoctogens. Okay, yeah. So roughly, this is your basic information on periodic table. So now, when we talk about periodic trends, what we're saying is there are certain similar properties which are notable. Because since these electrons are in the same group or same family, they may have similar trends. Okay, it's the same thing even in your homes where you come from. You say that, okay, in this family they are short. Okay, that's a trend. That's something that you can use to tell. Okay, or probably you can say due to similar chemical and physical properties, there are certain conclusions you can make. Okay, there are certain conclusions you can make as you move from top to bottom. What can happen? What is happening to the size? Okay, as you move from left to right, what is happening to the size? Okay, so you can make certain conclusions based on the similarity of chemical and physical properties of these elements. Okay, right. So we'll look at the first one, which is atomic radius. So the general trend as you move from top to bottom, okay? Here, atomic radius, whatever we're just implying the size of these atoms or ions, okay? General trend from top to bottom, size increases. From top to bottom of the group. And then across a period, size decreases. Okay, So meaning as you move, so if you pick one group, this is a group, as you move from top to bottom, size will be increasing. So you will notice a gradual increase in size. And as you move across a period, so I can pick one period, for instance, I pick this one, size will gradually decrease. And so on. So from top to bottom, size will increase from left to right on the period. The radius will decrease. So now you need to be able to explain. Okay, you need to be able to explain why. Why does the size increase? So here, size will increase. Remember I said you keep putting electrons in a new orbital, in a new energy level. So this one has energy level 1, but as you go to the next atom, electrons are occupying a new energy level of 3. So you notice that since you are filling new orbitals with electrons, it means the atom will be bigger in size. Okay, so 1 here, so okay, you say the first reason there is electrons are filled in higher energy levels. Okay, and since you are filling electrons in higher energy levels, there's also an aspect of effective nuclear charge. So the effective nuclear charge here, from top to bottom, is actually decreasing. Okay, so there is a reduction in effective nuclear charge. Okay, so you remember last time when I was trying to explain what nuclear charge, effective nuclear charge is. Okay, I'm mentioning that if this is your orbital and you have got inner energy levels, so this electron in the outermost shell, it will not feel the actual nuclear attractive force from the nucleus. Why? Because it is being screened or shielded by the inner electrons as well as by the electrons in its orbit. Okay? So, since these electrons are actually shielding this electron from feeling the actual attractive nuclear force, it means that what this electron will be feeling will just be for instance, a less attractive, a less nuclear force because of shielding effect as well as it's being screened. Okay, so effective nuclear charge is basically the force of attraction or the nuclear force an electron will feel when okay, the force of attraction the nucleus will feel in the absence of the inner electrons. Okay. Right, so this is on size. So I can write that here. Okay. So this is on atomic size and atomic radius. So from left to right, size decreases. Why? Because here we're feeding electrons in the same energy level. Okay? So since we are feeding electrons in the same energy level, there's actually a proton-electron ratio at play. Okay? There's a proton-electron ratio at play. Remember, electrons are in the orbitals, protons are in the nucleus. Okay? Protons are in the nucleus. So here there's a proton pulling power. Okay? So since electrons are in the same being filled, as we move from left to right, electrons are being filled in the same energy level. It means that the ratio between protons and, okay, or we can say there's a greater proton pulling power. There's a greater proton pulling power. Okay, so since there's greater proton pulling power, okay, it means that there's actually an increase in what? Effective nuclear charge. Effective nuclear charge, this is attractive force, okay, in the nucleus to the electrons. Okay, so effective nuclear charge. So the force of attraction between protons and electrons here will be increasing as we move from left to right. Therefore, these atoms will actually decrease in size because of increase in proton pulling power. Okay, so we move on to the next. We can look at ionization energy. Okay, ionization energy is the amount of energy required to remove the valency, to remove a valence electron, or to remove the most loosely bound electron. Okay, so as you move from top to bottom, we know that size increases. And if size increases, we also note that effective nuclear charge decreases. Effective nuclear charge decreases. So if the nuclear charge decreases, it means you don't need high energy to actually remove this electron from this atom. Okay, so we see that as you move from top to bottom, size is increasing, and if size is increasing, one, effective nuclear charge is decreasing. So the force of attraction between the nucleus and the electron in the valence shell here will be less. And since it will be less, it means it is easy to remove this electron. Therefore, ionization energy as you move from top to bottom will decrease. And then, as you move from left to right across a period, we note that size actually decreases. So if size is decreasing, we note that effective nuclear charge is increasing. So meaning the force of attraction between the nucleus and the electron in the valence shell is high here. High force of attraction. There's high force of attraction. And if there's high force of attraction, for you to remove this electron, you need high energy. That is why from left to right, okay, ionization energy increases. It increases. Okay. Please read more, refer to your notes, refer to your recommended textbooks so that you are able to understand these concepts. And then the last one we'll look at is on trends in electronegativity. This is ability of an atom to attract electrons to itself, or ability of an atom to attract electrons in a bond. Okay. That is what electronegativity is. And we now look at the trends in electronegativity. So from top to bottom, so we do the same. From top to bottom, the size increases. Okay. From left to right, the size decreases. Okay. So top to bottom size increases, meaning there is actually size is increasing. There is also decrease in nuclear charge. Okay. So for this atom to be able to attract electrons to itself, you have to look at the attractive force. Okay. So there is actually less. So here there's less force of attraction, less force of attraction for electrons as you move from top to bottom. Okay, then as you move from, so here there's decrease, electronegativity decreases from top to bottom, and then from left to right size decreases, and there's actually increase in proton pulling power, which is eventually the effective nuclear charge. So the force of attraction for electrons as you move from left to right, there is an increase in force of attraction for electrons. Therefore, electronegativity increases from left to right across a period. Okay, right. So please ensure that you go through your notes and prepare adequately for your exam. Okay. I mentioned that I taught you stoichiometry as well as atomic structure, and the last part which remained was just an emphasis on electronic configuration and periodic trends. So in this session, I was just trying to explain to you how you come up with electronic configuration and also how to explain the various periodic trends on the periodic table. Okay? Stay well and stay safe. Prepare for your exam. Any questions, please feel free to forward your questions and we'll be able to address them. Okay, bye for now.